So kindly solve this problem, Josh. Imagine a sophisticated watch mechanism where two gears are designed to interact in such a way that the motion traces out an epicycloid. The fixed gear has a radius of 5 centimeters and a smaller gear with a radius of 1 centimeter rolls around the outside of the fixed gear. A point on the circumference of the smaller gear is used to precisely position an intricate component in the watch based on the path of the epicycloid. Question: the component must be aligned precisely at the cusps of the epicycloid. Calculate the distance between consecutive cusps.
Okay, for the first solution, we're going to assume this what's the problem? The distance between consecutive cusps is here on the outside. So this, or most conveniently, this one, which is which is parallel to one of the axes, the y-axis. So first the R, the big R and the small r. So the big R is the radius of the larger gear, and then the small r, the radius of the smaller gear. And then here are the parametric equations for the epicycloid. So substituting, that's just 5 plus 1, 5 plus 1, and then 5 plus 1 over 1. So 6 cos t minus cos 60, and then 6 sin t minus sin 60. And it's graphed here, so this is how it looks like. So if there would be the circles, it would look like it. It would look like this, and then there's another circle here, like that.
Yes. Roll.
Anyway, so basically, the goal
circle
is to find any vertical line whatsoever, and actually just any vertical line that intersects the farthest points of the epicycloid. So if you draw, wait, I'm just going to open Desmos. If you draw this epicycloid and put a circle over it, t minus cos 60, 6 sin t minus sin 60. So that's one period, it's one cycloid. 2 pi, and then draw a circle over it, x squared plus pi squared equals 36, no, 49. Okay, so I think it's pretty clear that it's not perfectly symmetric. So as in this cusp is not at the perfect opposite x as the line here. So this is not negative of this. So it really has to be calculated. So clearly here, see, they're not on the same point. And the answer is about, let's do that, about
Not too fast.
wait,
That is
5
we want to inspect the solution.
7 pi, some 7 sin pi over 7. Or what is it? Anyway, ayun, there. So cosine pi over 7. So anyway, this is the correct answer. I'm just putting it here for reference. So this point on the circle is clearly not here. So they're not the same point. So it needs to be calculated. Anyway, so how to solve that? Maybe we could use derivative. So if it's apparent here, from here, the x is going up because it's moving this way, and then after this point it's going this way, and then here on this point it's actually irrelevant, but you can clearly see here on this arc it's going this way, so as in positive, but going here, actually wait, no, it's going this way since counterclockwise, so it's going negative the x, and then here it's becoming positive again. So what are these points? It's when it's 0. So the rate of change of the slope is 0. Of x is 0. So that just means dx over dt. So the derivative of x with respect to t. T is just the angle, I think. I presume it's the angle. Yes, it's the angle of wherever the point is. It's the parametric equation. So dx dt is just the derivative of x, which is 6 cos. So the cosine t becomes negative sine t, and then the 6 goes here, and then it turns in the negative will become positive, and then sine 60, nothing happens. That's just a chain rule. So anyway, this is the derivative. I'm going to graph that here. 6 sine t, or was it negative 6 sine t? Negative? Yes. Negative 6 sine t plus 6 sine 60 equals what if we make this y, maybe y x. No, that's not what I wanted. Maybe the opposite way, but anyway, equals 0 will work. Wait, if this is y, there. Now I'm going to put the correct answer, so we can just see where it is. X equals 7 cos pi over 7. There, so there's a direct point of contact.
That is 6 point.
So there are 3 solutions, here, here, and here, where yes, the derivative of x with respect to t is actually 0. So when is this true? So it's not easy to solve this normally. So normally you would expand the 60. That is painful because you have to do 2t, so that's the double angle formula, and they're going to do another double angle formula for 40, and then sine addition formula to get 60. That's feasible, but I don't think that's worth it. So what is noticeable here is both of these are sine and then times 6. So we can say that 6 sine 60 is equal to 6 sine t. So sine 60 is equal to sine t. What does this mean? So at 60 and at t, they have the same value, but sine is the y value, if you so to speak. So let's say this is t and then this is 60. So they have the same y value indeed. So what does that mean? I think it's pretty clear that this and this is actually supplementary. So these are the same using on just by inspection actually, but there are proofs. So t plus 60 is equal to pi, so we can say that this is just pi over 7 because t plus 60, 7t is equal to pi. So anyway, so now that we know the angle which is here, wait, I'm going to put it permanently, and then here t pi over 7, and then this one's negative pi over 7. So now that we know the t, we can always find the x and y. That's how the parametric equation works. You have an input value, only one, not 2 variables. So we can using this angle, we can find the x and y. So we are interested in the y because we are interested in this length, and then this length, and the fact that this is a perfect vertical line. So we can clearly say that this length is indeed this length. So its actual y value is already the half of the distance we want to find. So when t is equal to pi over 7, just substitute. So what did we conclude earlier? So sine 60 is equal to sine t. We're going to use this. But since it's on the opposite side, so that can be said to be minus 1 times sine pi over 7. So that's 5 sine pi over 7. Or another conclusion is, since these are equal, now we can also say that it is 6 plus 1. Since the sine 6 pi over 7 is equal to sine pi over 7, so we can now say they're like terms. So that's just sine of 7, no, this is cosine. Oh no. Okay, so anyway, the y is either 5 sine pi over 7 or 7 cos pi over 7. Doesn't really matter. So anyway, that was the y value here. So the other distance is just the y value of this point when t is equal to negative pi over 7. But we already know that the sign of negative x is equal to the negative sign of x. So this is just the same distance. So this whole distance from between the two cusps from outside is 2y. So since y is equal to 5 sine pi over 7, then 2y is equal to 10 sine pi over 7, and that's approximately 4.34. So just to check, let's do this. Approximately where is this point of contact? Let's say it's somewhere here. Yes, it's somewhere close to 2, maybe like somewhere in 2.13. Let me just show. Yes, so somewhere in the
put the point,
2.14, I can put a point. So somewhere in the 2.14 range, and the answer is 4.34. So almost there. By inspection, you can see that this is indeed the distance. But there is another definition of the cusp. So apparently, for some reason, the cusp is this place. So in everyday usage, we think the cusp is this part, but really it's not mathematically. So this is actually the cusp is a sharp point where the cycloid is set to change direction. So let's say when there's when there's a circle here, from going down, it will immediately go back up. So this is a point where there is no derivative. So anyway, here is the other definition. It's much easier actually. So this is just the original graph. I just put what I place in the side. I'm going to remove this because it's going to distract. So anyway, here is this point, the first cusp. And why is it at 5, 0 exactly? So let's say this is the circle, the large gear. It's not really a gear, but okay. Let's say it's a circle, and then the smaller circle is here. When it just starts, of course, then the point is at the very contact point. So it must be on the circumference of this larger circle. So of course that's just at 5, since the radius of the larger circle is at 5. And since it starts at 0, so 5, 0, simple. Okay, so this whole hypocycloid, it goes around at 2 pi. So since it's perfect, it's perfectly 5 to 1. So epicycloid.
Epicycloid.
So it's perfectly 5 to 1. So there would be exactly 5 cusps, and to traverse the entire circumference. So the entire circumference is 2 pi, of course. So 5 cusps for 2 pi. So the angle to reach one cusp should be 2 pi over 5. So 0 and then 2 pi over 5, 4 pi over 5, etc. until we reach 2 pi at the very end. So anyway, so it's clear that this angle is 2 pi over 5. And then I'm going to here. So where's the here? Good. So let's say this is a triangle. Actually, there's an easier way of doing it. There are two ways of doing it. Either you can say 2 pi over, this is 2 pi over 5. You can find this by just subtracting 2 pi and maybe over 2, yes. Or we can just say that since the remote angle, so this is 3 pi over 5, of course, to complete it, supplementary to 2 pi over 5. And then this must be half of the outside remote angle. So that is just 3 pi over 10 per these other sides, and it's isosceles actually, since this is just a radius. So Yes, so that's it. So we already find we can already find all three angles of the entire triangle. So why does this matter? Why do we need to find all of them? Actually, there's no need to do it, but I did it because there is a theorem. It's the sine law. So for any triangle A, B, C, and then their opposite a respective angles and gamma. Therefore, sine of alpha over A is equal to sine of beta over B. I'm not going to prove it here, but here is the theorem. So the sine law itself over C. So anyway, there are other ways probably of doing this. Maybe you could use a straight line approach from you have these two points and then you're just going to use the distance formula, but why not? That's not going to give an exact result. So anyway, here's the sine law. So we have the sine 2 pi over 5. So this angle, the sine of this angle over its opposite side, x. So that's this, and it's equal to either side, which we know this is 5 units because, of course, the circle just changed direction, so it must be on the circumference of the 5 radius larger circle. So that's 5, and this is also 5. So the sine of any of these angles over any of these sides, so over 5, and then we can conclude that x itself is equal to this. Sadly, I don't think there's a simplification for this, but anyway, where's the confirmation for this? 5 times over sine 2 pi over 5, and then sine 3 pi over 10. So about 5.8. So anyway, let's say we have a just to show x squared. I don't think that would actually be a good idea. Anyway, so just by inspection, actually, this is 5 units. Where's the triangle? Here, 5 units. Then maybe drawing a circle here, maybe there. Yes, so it makes sense. It's less than 6 units. So it's probably correct. So these are the two solutions. Actually, in the problem there is no single word that says outside or inside the epicycloid. It just says the distance between the consecutive cusps. So there are two solutions probably. This is the first interpretation where the distance is outside of the epicycloid, as in if you wrap a belt over the epicycloid, and here it's from inside the epicycloid. So for the first solution, the answer is 4.34 approximately 10 sine pi over 7. And then for the second solution, it's approximately 5.878. So that's it. Thanks for watching.
Thanks for watching.